Type in bang, welcome, bang.
Yeah, my ancient version of Safari.
What's up?
Hey.
I use Safari and comes back. I mean, Firefox.
Alright, does anyone have problems connecting to the internet? You solve all those issues? Did anyone not get pizza or sodas that wants it? Let me check the front kitchen a little bit.
You didn't know, okay. Good strength.
Free meetup chat. Is anyone not on the Discord? Aha. We got one person not on the Discord? Awesome. Yeah, it's not a problem. Welcome, by the way. We're gonna do names in a second. I wanna get you on the Discord though. So there's the geek way of doing this, which is the QR code, and I probably don't know that. Then there's the copy the link method of doing it. Hold on 1 second. We can do it here. So we click on this, we go down here to invite people, and then there's the link. Discord.gg/DHA capital V8VN. V8AVN. Did you get it? Oh, okay, I thought you had it. My bad. Let's see, invite people. Oh, great. Generate a new link. Let me see if I can do the QR code. I know I've seen someone else do it before. Is there a QR code thing? Maybe a mobile one. Let's see here.
Just copy that, put it in your QR code there.
Yeah. Should I do that?
That could like be with. Yeah, let's see.
I got this one. So I can All right. I think we kick it off. I'll probably have to leave a couple of times to pick up more people. There's always going to be some strangers that are out. If anyone has the Discord, who has the Discord open on their computer? There we go. We got notifications ready to rock. If you see someone message and say that they're at the door, just interrupt me and I'll go grab them. So we'll play that game for a little bit. All right. So we had requested to run another Rust class. We've done this before. This is the third or the fourth time we've done it because we've done it once post pandemic, and it's an interesting language. It's probably the language that I'm the most passionate about. It has a lot of really good, unique authors, and it's cool to share them, and it's also cool to see who can pick them up and then get a job in the industry. We have definitely some strong candidates in here that have pulled it off, you know. So what we're going to do is we're going to work through this book called the Rust Programming Language book. I'll tell you why I chose this book. This is not my favorite source material on Rust, right? This is the free source material on Rust. This is the canonical Rust book, right? So this is something that everyone reads, and it's nice because you can move through it at a relatively leisurely rate. It's not overly technical. There's nothing the concepts in here are not all that difficult to explain, and it does a pretty good job of doing it. If you want to become a Rust programmer and you are actually gearing that direction, I will refer you to a book called Programming Rust by O'Reilly, right? And I've done this on multiple occasions. Programming Rust by O'Reilly is, in my opinion, the best Rust book. It is a must-have if you're going to pursue this as a career. It will teach you with far more depth, and it'll be far more of a slog to go through. And it does cost you $40 or $50, you know. So it's not a huge expense, but it's far more thorough than what we're going to be doing here. This is going to be kind of like a high-level overview, and I'm not going to assume any background information. So if you've never done any programming at all, that's totally cool. We'll pick it up and we'll learn it with Rust. Rust is a little bit different than a lot of other languages, and I'm going to assume that most people here have had some experience with Python and JavaScript. So we'll pull some of that in, and I'll show you some examples of Python, JavaScript, and Perl, likely as we're doing this, to show you how Rust is different, what makes Rust unique. Let's talk about some of the resources. There is one other resource that is very popular with Rust. It's called Rustlings. And I'll go ahead and show you that here. Rustlings. There you go. And this is about everyone's sentiment. It's the greatest thing ever. People like this a lot. I'm a contributor on this project. And what this project did is it stole an idea from another language called Ruby, where they have, I think it's called Zen inside of it. And effectively, when you download Rustlings and you run Rustlings, it will ask you questions. It'll say, there's a problem with compilation, fix it, basically. And your program will compile. And it'll be your job to fix that. And as you start to learn how to fix these errors that other people have put in there strategically, you'll learn more and more about Rust. It's a really interesting way of teaching it. And to give you an idea, if you're experienced, you'll see these errors all the time, so you can go through them almost instantaneously. And if you have VS Code and you're a cheater programmer, or you've got fancy things like this, been lazy, it'll just pretty much tell you where the problem is these days. That wasn't around when we first created it, you know, but now it's everywhere. So it's worth acknowledging it. I want to say that if you're going to do Rustlings, you're probably better off not using that. You know, you want to kind of pick up an eye for where to spot these things and what's going on, rather than just rely on your editor to teach you all of this stuff. You know.
So don't use code.
No, use that whenever you're writing programs, when you're working on the book, that's totally fine. But Rustling's method of teaching you is to introduce errors. And obviously those errors are things your editor can find if you're using a language server. So you're cheating, you know, in my opinion. By all means, if you're cool with it,
Because the suggestions on how to fix it are too clear, like it leads you to web, like with MS Code.
yeah, it's stupid. It'll just tell you this is the problem, rearrange this piece of code, and you know, it defeats the purpose. But Rustlings is great, 5 stars. So if you need another free resource, check out Rustlings, and that'll help you get going. We will work through Rustlings, certainly, without a doubt. And we will probably do the vast majority of it in the class, right? We're not going to hit it up right away because the material is very easy. So I'll wait for us to get to an area where it's a little more hairy and people are exhausted. And then we'll do Rustlings because it's fun and entertaining. But by all means, if you've got the extra cycles, hit Rustlings up. I'm going to show you one more tool before we hit the book. And again, this is all stuff that I'm bringing in. You wouldn't find this if you were just reading a book. And that is called the Rust Search Extension. I'm a huge fan of this piece of technology. If you use Chrome, I highly suggest it. Basically, if I come over here and I click this guy, it opens up the Rust search extension. And this is an amazing productivity boost for me. Different languages cope with documentation in a unique fashion. Perl actually has a remarkably good way of coping with it, and it's very antiquated. Some languages have no way of coping with it, and you see like a hit in productivity for that. This is more or less Rust's way of dealing with it, right? So Rust has an ecosystem that is heavily dependent on external code that other people write. This is a really nice way of seeing that code, right? So for instance, if I want to find documentation on something I'm using, like clap, I would type literally rs space and then exclamation point clap, right? And it's going to open up the external crate for clap and show me the documentation. There's all kinds of cool stuff the Rust search extension can do. By all means, download it, give it a shot. You'll see me using it a bunch, and I don't want anyone to think that I wasn't telling you my secrets, so now you know. And if anyone has any questions about what I'm doing and how I'm doing it so fast, just ask me what the hell I just typed in, and I'm happy to explain it, you know. But that's what I'll be using to facilitate navigating documentation, external code, all the other kind of stuff. And Rustlings is also pretty good. One other thing, thank you for recording this. We had a lot of people asking questions on that, so it's always good to see that someone's going to have videos up. I believe you also did you do the last videos too? The last Rust course? There we go. So we don't have the earlier videos from the last Rust course, but we get to like 3 or 4, you'll even have 2 to choose from. Come on in. Welcome back, Caroline.
Hey, I brought.
Your brother?
Yep.
Yeah, you told me you're going to whip him into shape, huh? You turn him into a programmer?
We'll see.
That's
First,
it. Caroline is our resident fencing expert. So, yeah, that's a special skill. All right, so I said we're going to kick it off. Before we do that, let's also do names, right? It's going to be there's obviously landing faces, so you may actually do this more than once, but if you could just stand up and say your name, and let's just go down the aisle and in that direction. And then at least I'll have something to go on, because I didn't bring name tags. I'm cheating. We got a Josh. Josh is silent. Josh does pretty good talks in places we can't mention. And you should talk to Josh later about his good talks.
Hi, I'm Sam.
Very cool. Sam, you said you just now joined Discord. How'd you find out about the group? Josh, there we go. Josh already recruited. +1 H-Luck points. Start over here.
My name's Alex.
Very cool. Alex was my old manager. Wherever he gets a job next, you should apply. I give him my promotion there. Go on.
I'm Vaughn.
Very cool. Vaughn, is this your first time in H-Luck?
Yes.
How'd you find out about it?
Places you can't mention.
Places, okay, very good.
Places.
Yeah, okay.
I'm Robert.
Robert, awesome.
Hi, I'm Dalton.
Yeah.
Hello, I'm Dina.
All right, we're swinging back over here.
My name is Khan.
Very cool. Con, you're a new face. How'd you find out about H-Luck?
You reached out to me on LinkedIn.
Boom, there we go. Bringing the good word one person at a time. Did you get a personalized message?
I don't know.
Or was it super canned?
I'm not sure. You sent me the Discord link and I joined it. And
Badass, there we go. So you couldn't even tell that it was a super canned message. That's fucking
It's
smooth.
been a while.
No, I pestered everyone on LinkedIn I could. So that's awesome. I'm glad to see you.
Hi, I'm Sam.
Arash. Marco.
Marco.
Tony.
Tony.
Yeah, Rob.
You can start on the other side. You can break the trend. What was it?
I'm Rob.
Rob.
Caroline.
Caroline.
Carroll's.
One more time. Say it again. You know your name. You don't have to leave your sister.
It's Charles.
Charles. There we go. All right.
Isaac.
Isaac. Awesome. You want to go? No.
Two.
There we go. Okay. By the way, is it who or Chu? Chu. Chu does thousands of videos. He has the largest collection of Houston videography you'll ever see. Like, I follow Chu on YouTube, and I am shocked at the amount of content you create. Everywhere in Houston Tech, search So, cool. Let's go ahead and hit this up. We already gave the introduction there. The foreword doesn't sound all that important. Let's skip that. Sure, it's a charming story. All right, who this is for? Students. That's going to be some of the people here. Companies. Hopefully that's none of the people here. At least you're lacking ties. You're just, what's up? Ah, yes. Good. By the way, those are things that I appreciate when you're shouted out. Companies, open source developers, obviously. People who value speed and stability. Who this book is for, how to use this book. This is not all that important. We're going to use this book, so this book is for you, and that's all that matters. Yeah, I may have a little more to add about who this is for as a language. Getting started. So we're going to start with something very easy here, installing Rust on Linux, macOS, and Windows, and writing a program that prints hello world. This is kind of your very short thing that everyone starts with. Installation. Quick show of hands, I did a shout out in the Rust channel, and I've helped on this at last week's meetup. Does anyone here not have Rust installed? Okay, so this installation thing is absolutely prime. You're going to want to do this. Why don't we go ahead and start with that? It's one line, right? It's going to be right down here, this curl command. Are you running Linux? No?
Yeah.
Yes. Good. We'll get you there. We still have some conversions to do. There is advice here for installing on Windows. There we go. Rust up on Windows. So you're going to go to this website, rust-lang.org, tools install, and that's how you'll install it. And what we'll do on this, because I've never installed it on Windows and I don't know what kind of difficulties you can run into, I'd suggest doing it now. And then if we have difficulties, either after the class today or we get to a stopping point, we'll hit it up. Marco?
Did you put the link to the website that you're using right now on Discord already?
It's on the Rust channel.
I believe it's in the Rust channel.
Oh, is it the top? I see it now.
I pin them.
You're.
You could do rust up dot dash dash book, and then it'll pop it up on the URL.
Cool.
Search Rust and it's the first thing that pops up.
Huh.
I just googled rust book.
Yeah, that's another way to do it. That's how I actually get to it. I just Google Rust book. It's the big one. All right, updating and installing. This is kind of cool. Let's talk about this for a second. Rust comes with an installer and a maintenance system for the actual Rust binary itself. So you kind of have two different things here. You have the things you install with Rust, which we use Cargo for, and then we have the thing that we use to install Rust, which we call Rust up. There's different ways of getting Rust up. Rust up is easily the most popular method. And if you have Rust on your computer and you're running it on nightly or you're running it on stable and they release a new version and you go, I want that cool stuff, you run Rust up update and it'll download you a new version of Rust. But it'll even do you one better. Because when it downloads you a new version of Rust, you have a new standard library, so it will recompile all of the global Rust things you've installed. So it works with that. So it's nice to lean on that tool. It's a good thing it has it. I wish other languages did this, but they don't. All right. Yeah. So what they're showing you here is one method of creating a project, right? And then inside of that project, they are going to create a hello world script, right? And they're going to call it main.rs. I would say you will never do that in Rust, right? This is important to see that you can do it, that it really is that easy, right? You can create a file, main.rs, and you can run rustc against it, like they're doing here. And this will work, right? But you'll never actually do that as a Rust programmer. You do this with Python, you create like test.py and you write Python code and you give it to Python. Do the same thing with Perl. You don't ever do that with Rust, because with Rust, you have Cargo. It's part of the core. And we use Cargo to scaffold us out either binaries or library projects. And those binary or library projects have all of that stuff done, right? So you always work inside of this scaffolded Cargo project. And the advantage of that is that when you want to give that code back to someone, it's already in the format that they'll accept it, right? So you look at some other established companies, which won't name them all, but they don't have a method of like compartmentalizing the code that they write. It's all part of one big monolith. With Rust, it encourages you running cargo new. Cargo new. It's going to become like second nature to you. And when you run cargo new, it'll do all of this stuff for you, right? So they're showing you can make a directory called projects, you can make a directory called hello world in it, you can add a main.rs file in it, you can write Rust code, but effectively that's a gigantic waste of time, right? Let's examine what they're calling the anatomy of the Rust program. They're saying that Rust starts with a function called main, right? This is something that you see in compiled languages. They have to say this is the entry point, right? Languages like Perl and Python and Ruby, you can write whatever shit you want in them, like print, outside of a function, and it'll just run it from top to the bottom, right? But a lot of compiled languages, they want to have a specifically named function, main or something like that, and then you write code in that function, and then they get compiled and something calls into that function. That's what runs it. So every Rust program will have function main somewhere in it. The only exception to that are libraries, where someone else is using your code, and you don't need a main, because they decide what happens. All right. When it comes to printing out in Rust, we have a slightly different syntax than you'll see in most languages. We use println, right? This is probably not a shock for you, print line, very simple. But the exclamation point afterward is probably a little bit of a shock. You've probably never seen that before. And this is a Rustism. This is something new that Rust brought, right? In Rust, we differentiate between functions and macros. And there's a reason why we do that too. Macros don't exist when things get compiled, right? So a macro can be very complex in what it looks to be doing, and you don't spend any of the cost in having it do that, because that work happens in compilation. It doesn't exist, right? So let's say that you have a print line and you give one of them an integer. It's a 5, right? But it's not a string of 5, it's a number 5. Rust has to say, I need to take that integer and generate a print line function that can read an integer. If you don't have one that is providing a print line and integer, Rust may say, I don't even need to generate it. I don't need to convert integers to strings, right? Because you're not doing that. So by keeping it in a macro, we can eliminate the size of that output. When you build it this way, they're providing main.rs to Rust C. It's nice to know that Rust C exists, but this is another internal thing that you'll never need to know or use, right? So if we come down here and I go man Rust C, you're going to see a ton of options on it, right? These are all related to how you can compile things with Rust. And this is similar to like GCC for C. This is a compiler, right? But it's not how you will interface with the compiler. You're going to interface with the compiler with cargo build. So you'll just simply never do this, right? And I'm just saying this is complexity that doesn't matter, but they're trying to introduce you. All right, now here's where I think we get down to the bread and the butter, right? This is where they're introducing cargo. So now we're not in the esoteric method anymore. Let's take it, and I'm going to back out here, and I'm going to remove food. And now we're going to look at cargo. So if I run cargo -- version, right, you're going to see that I'm on cargo 1.8.0 nightly. I stay on nightly Rust when I do it. And that's pretty normal. A lot of the professional developers stay on nightly. And cargo is how we do everything. So now we say cargo new, hello cargo, and they're jumping into cargo. And this is exactly how you will use it, right? So now we went from doing something that looked pretty simple and it looked pretty routine. It's what we see in other languages. And I'm telling you, it's even easier than that. Now we're looking at this example, and it's literally cargo new hello world. And I'm telling you, even experienced Rust programmers, that's literally all there is to it. That's going to create you the library. Cargo new hello cargo, right? Well, the binary. And it says here, creating binary application, hello cargo package. Right, now I can jump into hello cargo, and you're going to see it's already scaffolded. Right, it already created the Git repository for me. It already created the cargo toml file, and it already has the source main.rs. You can see at the bottom. All right, so let's go over some of that. I'll blow it up a little bit. Cargo toml is kind of like how we introduce the Rust package, right? It tells us things like the name, the version, the edition. That's going to be what variant of Rust it requires. Rust C is versioned with numbers, 1, 2, 3. Those numbers support different editions, 2016, 2018, 2021, right? Here's the deal. Because you have Rust C never breaking backwards compatibility thus far, it supports every prior edition. So this is really kind of cool. This is a trick Rust does. I'm being careful the way I'm wording it because I don't want to lie to you about what's happening. But it effectively means that any edition of Rust is supported by any modern version of Rust C. So you can compile code made for Rust 2016 on a modern version of Rust. All you do is change your edition to Rust 2016. It'll work fine, right? This is nice. So it's forwards compatible thus far since the start of Rust, right? May not always be that way, but right now it's been that way. So this is how Rust evolves as a language. Yes?
Your screen is getting cut off at the top.
Thank you for pointing that out. Appreciate that. Good looking out. All right. That's what we got. The version is your version of your program. And Rust also makes this, by the way, I love that laptop. Is that the X60 or the X230?
201.
201. I have that too. Cool. That is a geek-ass laptop. Anyway, so what we have here is the version number is Semvar, right? Quick show of hands if you've ever seen Semvar or you know what Semvar is. Okay, actually, it's a new concept, so let's explain this. Versioning used to be something that everyone had a different way of doing. It was an art, right? And the problem was you couldn't communicate with it. So some people had beautiful versioning schemes, and some people had really wacky-ass versioning schemes, and it was always difficult to figure out which version was newer, which version you should get, which version had, all of this stuff was just questions. It was different on every project. Semvar came around probably 10 years ago, maybe a little more than that, and it totally wiped out all the other versioning methods, right? And I would say that for new projects, only the insane don't use Semvar, right? So if you're sane, use Semvar. And how it works is very simple. Is we have three different numbers, and when you're looking at it, the number on the left is called the major number. The number in the middle is called the minor number, and the number on the right is your patch number, right, or your bug fix number. And what that means is, if I look at this one at 0.1.0, right, if I release 1.0, I may have broken changes with this, because it's a new major number. 1.0.0 has a new major number. And if I release a 2.0.0, you know I have definitely made breaking changes, because that's the definition. You bump the first number. It's a little undefined when you're at 0.1, I'll be honest. Right? Like that's a question. When you release the first version to the world, you're supposed to go 1.0, regardless of whether or not you introduce a breaking change. But if you see the first number change, you go from 2 to 3, 3 to 4, that first number on the left changes, you have a breaking change. That means you need to retest shit. So if you have a QA, you throw it to them, or you monkey around with it. Make sure that that library still works with your code. Now, Rust has a real leg up compared to a lot of other languages because when Rust breaks things, they break something with you. Very frequently, it shows up in the contract in the code. So the Rust compiler will come back and say, I can't make sense out of that. This function now isn't there. It's a different argument. You're not providing it the right argument. It's returning a different type of value. You don't know what to do with that value. It'll tell you where the problems are. So in Rust, you're safer ignoring it, but you shouldn't ignore it, you know? The second number is minor, and that just means someone has implemented more functionality, right? So maybe they haven't changed anything, but now your new widget can do cooler, newer things, right? So that's the minor number. And the third number is a bug fix number. That means we haven't implemented new functionality, but we have fixed a bug, right? Now here's the catch. That could be a security vulnerability, or it could be a bug in the user interface. Semvar doesn't tell the difference. But understanding this is absolutely prime if you're going to go into any form of tech. Because if you're in systems administration, you're going to have to know how to upgrade your stuff, what's going to break and what's not. And if you're in development, you've got to know how to read these numbers from your dependencies.
How do you spell Semvar?
S-E-M-V-A-R, Semvar. It stands for semantic versioning. And the reason why it's said to be semantic versioning is because before that, we would literally say, well, this feels like a big change, so let's bump the big number, you know? And Semvar says, no, it doesn't make a difference how you feel. Bump the big number when you're breaking something, you know? And this is why Linux is still version, whatever, 4, or I don't know what they're these days, but you don't see these numbers change much on Linux, and because they're not a Semvar system. They've rejected Semvar. All right. So they still do that. They say, when are we going to bump to the next version? And then they all argue. the addition, I already explained that, and then the name, yeah, for now, let's just assume the name is the same as the outside directory. That'll be good. All right. Okay, the println, we already went over that, that's a macro. Now building, right? I told you earlier, you're never going to use Rust C because it's too low level, it's too direct. You're always going to interface with the compiler with Cargo, right? Let's see what that looks like. If I come down here, this is the program, right? And if I exit out of it, let's see, what jobs do I have? Okay, I have skill wall. Let's take a look at this 1 second. This is the main file in it. So this right here, this is what Cargo scaffolded in to show us test code. Cargo already does that. When you create a binary, it just does this as your scaffold code, right? It says println hello world. That's your scaffold. So if what it's showing you here is that you can compile this. So when you run Cargo new, you already have a program that can be compiled. And to build it, all you're going to do is run Cargo build, and it's done, right? Now Cargo build is going to put that thing you just built under target, under debug, right there, hello Cargo. Now, let's make a couple of different distinctions here. Cargo build compiles the program, it doesn't run it, right? There are two different methods of compiling every Rust program. There's the debug method, which is the default. This is going to tell you, when you're developing it, where the problems are. It'll give you more information, right? It'll also tell you, it'll catch more errors, because it'll implement bounds checking and things like that in runtime. Make your program run a little bit slower, but it'll say, hey, you overflowed something. There's a bounds problem in this. The alternative to debugging, to a debug build, is a production build. And to do that, we just do cargo build -- prod, right? So if I go down here and I do cargo build release, cargo build -- release, right? Now it's going to say here, finished profile optimized target. So this is an optimized one, right? So we can look at the two. Cargo build, it's going to say unoptimized plus the bug info. Cargo build -- release, profile optimized target, right? Both of these are going to be in target. So now we have a debug folder and a release folder. And we can even see the difference in the size. It's usually pretty obvious, right? So if I do this here, you're going to see that the debug build is 3.5 megabytes to say hello world. And the release build is, 400K. So it's 1/10 the size, right? That's pretty normal. You'll see release literally drop off 90% of your size, right? By not having the debug information. Okay, now we have two different methods we can use to run it. We can either explicitly give the path to that executable we just built, right? Like I can say right here, target release hello cargo. That will work, and it'll tell me hello world. But the way that you'll more often do as a programmer is you'll run cargo run, like that. And then it'll just tell you hello world. So cargo build builds it, puts it in there for you. Cargo run runs it right away. And this is nice because people often say, well, why would I want to use Rust? You know, and they get into this very semantic argument of I don't want to compile things. But what they don't realize is most languages already have compilation built into them. They just abstract it from it. Perl also compiles things in a way, right? So you can run cargo run and give it code, and it will run it on the fly, right? For you, just like anything else will. And in many aspects, it's quick enough where it doesn't make a difference. The fact that it's compiling is in fact going to make it slower than an interpreted language, which doesn't have to do all of that kind of work. But it's quick enough to where it doesn't matter for you. So make cargo run your friend. I use it for all kinds of stuff. Cool. Now we have cargo check. Cargo check is interesting. Now, this is also, I think, a generational thing. You will probably not use cargo check that much, right? I could say that it's probably dead. Because the development method in which you used cargo check is gone. What we used to do is we would check our code outside of the editor. We would go down to the shell, we'd run cargo check and say, these are where all the problems are for your code. And then we go back into the editor and we fix the code. And we could do it really quick. It was nice and effective. No problem with it. Now everyone has language servers built into their editor. It is everywhere. I imagine the vast majority of you are using VS Code. There's probably not a single person in this group that's using Emacs. And if you're using Vim, you probably have LSP built in. So cargo check isn't needed because when shit doesn't work, it's gonna write up, pop it in red. You're gonna see it pop on your screen and say, there's a problem here, you need to fix it. So before you even run cargo check, you'll know that there's a problem. But yes, you can do it the old way, you can run cargo check. And if you do it and there's no problem, we'll see something like this. And let's take a look at what happens when I break it, right? Let's come down here, let's break it, let's remove the exclamation point. Now, right away, it's giving me the red X right here, right? So I already know that there's a problem in the editor, and it even tells me what the problem is. Expected function. Found macro println, it's not a function. So it's telling me that the thing it found was a macro, and I'm trying to call it as if it was a function. I don't have the exclamation point. If I run cargo check, it'll say the same thing right here. Could not compile. Help use blank to invoke a macro, right? So it's telling me the problem too. So cargo check is another way to get that information. But now that we have it built into our editor, all that we do is it gives us the red box and we do the red thing. Or you integrate it into ChatGPT or whatever the fuck people use these days. It probably just automatically fixes all this shit. There we go. Yeah, GitHub, Copilot, GitLab Duo, whatever. Capitalists want to make sure no one has a job. Trying your best. All right. So, cargo is a convention. Yes, I agree with this. Cargo doesn't provide a lot of value over Rust C, but it provides enough simplification to where you'll never use Rust C. I agree with you. And you can, when you take a Rust crate that's published on GitHub and you download it, there's already going to be a cargo file in it. Cargo.toml already exists. So when you want to compile Rust programs, no matter how complex they are, you're going to use the same command, right? So there's a lot of like really cool and complex Rust programs. And if you want to play around with them, you can. You can actually download them. And all you're going to do is run cargo build. It is almost never with Rust more complex than running cargo build. Absolutely. No, you can have it. Make an exception.
So you never run into like weird esoteric GCC flags?
So let's talk about that for a second. That's a high-level question, but let's hit on it, right? You said you never run into esoteric GCC flags with Rust. The answer is no, and the reason for that is because Rust tends not to use any non-Rust code. This has got its pluses and its downsides. The downside is if you're really into benchmarks, you can make an argument that Rust is slower because of it. Rust, generally speaking, doesn't care. They care only about safety. So the fact that their shit may be slightly slower doesn't really bother them much. And it's generally not a big enough difference for them to care. The upside is Rust is a ridiculously large community. And their code, in my opinion, even when they recreate the biggest absurd projects that you can find in software, is better than the code that preceded it. Give you a great example, OpenSSL. OpenSSL is a pain in the ass for everyone that's not Rust, because you have to have this OpenSSL library, then you pull it into your program, then you find out the cipher list is different. It's just a mess, right? Rust uses something called Rust TLS, right? It has all of the TLS functionality that's needed with OpenSSL, and you don't have to do anything. So if you download a program, a Rust program, the default is going to be to ignore OpenSSL entirely, to compile with Rust TLS. So the answer, you ever need esoteric flags? No, because there is almost never going to be anything you build against that's C. Very few exceptions to that. Rust has literally recreated mostly everything, you know? And again, whether or not that's a good thing, that's a philosophical argument. I will just say remarkably effective, and much of the code simply has less legacy stuff. But also, one other thing to say is very frequently when Rust does recreate something, the whole rest of the world jumps on it, and then it's the new next big thing, right? So there's a huge precedent for Rust displacing old C programs with better and safer code because they decided to recreate it in Rust. And in fact, one thing Rust will do, this is the hardest language there is in computer science. There's no, just easily, if you exclude esoteric languages and you're just focusing on what you can do with production. This is a hard language, that's why we do this class slowly. But I would say that yeah, I'll leave it alone. We'll go back to that in a bit. I'll show you some more stuff on that later. But let's make the joke. There's a gigantic movement amongst Rust users that have elevated their ego for having learned Rust, where they will open up issues on third-party trackers, and they call it rewrite it in Rust, right? So you just go in with a gigantic fucking ego, right? And you file an issue on whatever is the most popular product you can find on GitHub, and you say, this is a beautiful project, but you should rewrite it in Rust. There's a horrible precedent of Rust people doing it. It's hilarious. I definitely had my days doing it too, a long, long time ago. It's funny, and it's also interesting too, because very frequently people will either they'll close the ticket right away, right? Or they'll close the ticket right away, and then years later they'll come back and they'll actually fucking do it, you know? And there's quite a few examples where rewrite it in Rust has actually worked, you know? It's bizarre, but they'll come back 5 years later, they'll be like, okay, we finally rewrote this in Rust, it was a good call. So the rewrite it in Rust campaign, if you're interested in trolling social drama, it's entertaining. All right, so what we're gonna do now is we're gonna build a guessing game. And when we do the guessing game, we're gonna go cargo new, so we're gonna build with cargo, right? Let's go ahead and do this. I'm gonna delete hello cargo, and we're gonna go cargo new, and then I'm gonna say here, guessing game. Now we have guessing game created. And now what we're going to do is we're going to iteratively make this guessing game better and more effective at being a game. So the first thing that they're doing is they're showing you what is already created, and it's nothing different than we had before, except the package name is now guessing game. So we are going to build it up here, processing a guess. Okay, let's talk about this for a second. Rust has a standard library, just like most languages, std.io. You will almost always use it. It is a remarkably good standard library. std.io is just like in C or C++. That's how you're going to interact with the user. Print things to the terminal, read things from the terminal, that kind of stuff. So it is what provides this, IO stdin, standard in, right? Standard in is just a convention for saying I want to read something from the terminal. Your terminal, when you open it up, has 3 different streams of data coming at you. There's standard in, which is what you read from the terminal. There's standard out, which is what you print to the terminal. And then there's standard error, which is any kind of error your computer program generates. You usually redirect that to a file. And what we're doing here is I'm creating a new string called guess, and then I'm telling it I want to fill this string up with data from the terminal. So I'm calling IO standard in, and I'm saying read line into this mutable guess. And then if I fail, I say fail to read line, and then otherwise I print out what the guess is. So this is very simple. We're asking one question, we're saving it in a string, and we're printing it out as the answer, right?
Video promote.
No. God's are angry. Okay. Knock that down a little bit. Oh, see, whenever I write it, my editor says you have blank lines at the top, and then it just removes them. And why I'm doing that is so we can all see it, because it's getting cut off. So that may work. There we go. There. Okay, now it's good. All right, so let's take a look at that. That's the code right there. And now when I run this code, that is going to work. Right? It's just going to read data, print it out. Let's take a look at this here, the syntax for print line. This is kind of interesting. The curly brackets are a way to templatize where you're storing that variable. And I'm just giving it the variable on the inside. So that's how you do that in Rust. Different languages have a different method of doing it. Let's go ahead and pick up that lesson too. So now I'm going to go cargo run, right? And it's going to say, please input your guess a number. I'm going to give it 42. It's going to say, you guessed 42. That's it. That's all there is to it. Now that's a pretty shitty guessing game because normally it should generate a number, and then I should generate a guess, and then it tells me whether or not I'm right or wrong, and tells me hot or cold or something, right? So what we're gonna do is look at this, and that'll probably be the next evolution of it. They're gonna explain it. Yeah, let's go over the mutability of it. That's a good idea. Point that out. Okay. So if you look here on line 4, that's a horrible numbers. Anyway, that's how LazyBook does it. The line numbered 4.
It's 4 above where your cursor is.
Yeah, I know.
Cursor.
But if I say line 10, that's gonna be really not useful, right?
Well, yeah.
So, I don't know row numbers. Yeah, I just turn off row number, I guess, right? Set no row number.
Watch video for a moment, twice. Like whatever you're doing.
There we go. Okay, I guess I can do that.
Good, there you go.
Okay.
I've watched video like 5 times in the last 10 seconds.
Oh.
It's gonna be a not great HD line.
Yeah.
No, it's just I've been used so much, it's probably short out in your.
Yeah. I don't know what's going on here. I've had that problem here before. Maybe we should bring one more. All right, so what I want to hit on here is the difference between a mutable variable and a not mutable variable. In other languages, mutability is your default. So when you create a variable, almost always that variable is mutable. Perl, Python, Ruby, PHP, all of them. There is JavaScript too. There is no default immutability. In JavaScript, you do it by declaring the variable a constant. If you ever seen something like const, that means that the variable cannot be rewritten to. Here, we do it with mute. So mute essentially says that that variable can be written to, right? Rust has a whole entire level of complexity around mutability. And it does that because in making these concepts more explicit for you and for the compiler, you can save the compiler from having to do crazy things that are slow, right? So if you have immutable data, think about it like this. I'll give you a very high level overview of where like mutability becomes a thing. If you have immutable data, right, and I want to provide that data to 10 different functions, I can tell the compiler do it all at the same time, right? Because the input isn't going to change. So I can give all 10 of those functions the same input, the same reference to the input, and they'll all work, and I can have them all do it in parallel. But if it's mutable, suddenly we could have a race condition. Which one's going to write to it first? Which one's going to write to it second? You can't have two things receive mutable data that have the potential to write to it. So by making things immutable by default, you have a lot more speed advantages. Things become easier when you write advanced programs, even though you got to learn the shit now, right? You have to start to think about things in a way you're probably not used to.
Just using the.
I'm comparing it to using dynamic typing. Yeah, this is not dynamic typing.
It's not.
No, it's not. So this is actually saying here, you are declaring a string type, right? So let you guess equals string new. String new is returning a string type. That is a new function on a string struct. It's returning a string type. Now, you may say, why isn't the type? What's up?
Wouldn't it type be on the variable side? though?
Okay.
Usually I've seen like colon string on yes side.
Let me get there. Okay. Yeah, but you're exactly right. So, but you're wrong on what you call it. Way wrong. So let's cover that, right? Because that is true. We don't write the typing information you see in a lot of strongly typed languages. So the question is, we're creating this thing called string new, right? But we're never saying that guess is a string. So what if you have something different and you're assigning it to guess? Guess. It'll work just fine, right? The reason is not because it's dynamically typed. The reason is because it's type inferred. This is a gigantic, epic difference, right? Rust makes strong typing easier. I like that. Easier than it may otherwise be because it has very, very good type inference. So in many cases, Rust can figure out what your types are by what the thing on the other side is returning. It knows that guessed is being set by a call to string new. So the compiler says, what is string new returning? That's what I need guess to be. And forever, it's that type, right? Let me give you a case in point. It's mutable, right? So if I do guess equals 42, this is gonna fail. Mismatched types, expected string found integer. It has inferred the string type. You have said, here is an integer, and it has said, you know, that's a world of pain. We're not doing that. So we're not dynamically typed, we're type inferred. And this This is nice. You'll see this everywhere. And you should always think about that difference in your head. You know, what is the type it's inferring, all of that other kind of stuff. Now, some people would say, well, can we be explicit if we want? Yes. There's nothing against you being explicit. No one will critique you for doing that. It's a little bit of extra typing, and it's somewhat unusual, but there you go. Now we're explicit. Now we're saying, let this mutable type called guess of type string be set by a call to string new. Right? But that's how most languages did it until Rust came along and made that a little bit easier. Haskell also has typing. All right. We went over immutability, we went over standard in. Let's go over the expect part. This is also a really cool thing. Different languages organize themselves in a fashion that is consistent in the language and makes it convenient. All right? I'll give you a case in point. When you write Python programs, you tend to think about iteration all the time. It's in the back of your head as a Python programmer. That's what makes a Python programmer different from a Perl programmer. If a Perl programmer learns about intervals, they make a good Python programmer. It's really the only difference. So the notion of iterables is that you start to think, can I iterate over this thing? And what would it look like if I did? That's a way you decompose a problem in Python. So if you run a query on a database and it gives you back a result set, right? And you iterate over that result set, what would you get back? Anyone use a database? You get a result set back in Python and you iterate over the result set, what do you get back? You get back a row, typically, right? You get back a row. You get one instance, one thing out of that result set. So you start to think a result set returns many rows. When I iterate over it, each time I get something, I'm going to get a row. That's how you break a Python problem down. Rust has got all of that, which makes it very nice. That's why a lot of people think it's a beautiful language. But one area that Rust, I think, is especially beautiful is this area. And this is how Rust handles errors. Rust is in your face about errors. It doesn't give you the option to ignore an error implicitly. It makes you be explicit when you ignore an error, right? So readline is returning what we call a result in Rust. A result always is one of two things. It's either a success, okay, or it's an error, right? One of those two things. And both of those things, a success or an error, can have a value. You can have a value representing an error object. You can have a value representing a success side. But those two things have to be distinctly named from everything that returns the result, right? So you always know this was success, this was error, and you don't ever have to question it. Now this is where Rust, I think, has one-upped a lot of the competition. Readline is returning a result. What happens if it's an error? Rust will not let you compile the program without addressing that question. It makes sure you have that error handled. And one way in which you can handle that error is with expect. Expect says, if I get an error, don't pass it up, but panic and give it this string. Failed to readline. Game over. That's one way you can handle an error. So whenever you get an error back in Rust, you don't ever have to, you will never accidentally ignore it. You can, but the semantics on main are special. The semantics on all of the other functions are not special, right? And effectively that's because, let's say that you have an error and you want to return it in main. It doesn't make sense. There's nothing above you to handle the error. So when you go down and you say, how do I handle an error? Can I return the error? Of course, right? Make the function a result. You can return the error. You can let it bubble up. That's the JavaScript word for that. Let something else catch it. But when you're at the very top, you're in main, how do you handle an error? If you still have an error at that point, you got to do something with it, right? And expect is one way to do it. Crash the program.
If you remove the expect, the program will still compile and run.
No. It'll give you an error. Well, maybe it's only warning. Yep, okay. Unused result, that must be used. I thought that was related to an error. I would never let that compile anyway. So yes, it is only a warning. I take it back. It's not an error, but it's still an explicit warning.
Another question, how come the read line has to take a mute to the guess? How come if you remove the mute?
Okay, let's see here. If I remove this mute here,
No. And the read line, it has a mute.
okay.
It won't work, right?
It will not work, right? And that is because the reference is different from the actual thing you're pointing to. If you have a mutable piece of data, right, but you have an immutable reference to it, you could still pass it off to other things that you know aren't going to read and write to it, right? So if I remove this, it should just error. Or, it's going to say here, read line expects immutable string. And the reason is, read line can't write without mutability. So the requirement of read line is you give it a mutable reference to a string and it can write to. That's how this works, right? In some languages, let's step back just 1 second and explain why this is weird, right? Because this may be a little bit weird. In some languages, you would do something like this, right? Here, that's Python. Right, let's click on Python. In Python, you do something like that, right there. A equals input, quote, hello. Right? That's Python, will read it from the screen, tell you hello, and you give an answer. The problem with that is that A, it doesn't say anything about who owns A. It doesn't say about anything about where A is stored. It doesn't say anything about how A gets freed. Python doesn't worry about this. This is one of the reasons why Rust is faster. So in Rust, something has to own it, right? Something has to own that block of memory. And when I come up here and I say let mutable guess of type string equal string new, I am saying that function main owns that data. I'm letting something else write to it, but that thing that writes to it can't destroy it or delete it. That's my job. I own it. So I'm giving it a mutable reference to write to, but it cannot destroy that thing. That's my memory. So there's this distinct notion of ownership, and you'll see this a lot in Rust. You will pass a mutable reference to something, it will write to it, and you will retain ownership of it, right? And this gets you out of that loop where if that thing, if input owns the data, and the second you're done with the call, the data goes away. It's cleaned up. Something external has got to own it. We're going to cover this exhaustively in like chapter 5. So this is coming up. This is the one hairy chapter in this whole Rust thing, in my opinion, is the one on the borrow checker and ownership and all that other kind of stuff. All right. But I want to make sure that you're all on board with this, Arash. We are telling it explicitly, we're giving it a mutable reference to our data, and it is giving us a result back. That's what it's giving us back. It is not giving us our data back. It's writing to the reference and giving us a result back. That result is either going to say, I wrote to your reference fine, or there was an error. And if there was an error, I'm going to elevate it, crash, and say failed to read line. All right. For a run, there's my guess, and it works, doesn't have to be a number. Okay. Okay, let's hit on this too. Let's get down to this one, because this is nice. We already showed that we get a warning if we don't handle the error, right? The potential error result. But there's other ways of handling that, right? So this is a shorthand we often use when we're debugging code or we want to ignore things. You can say let underscore equals like that. Now I'm assigning the result to that underscore variable, right? Which is nomenclature for I don't care about it. It should never be used. And because I'm not discarding the error, Rust is fine with it. That's totally okay. So this, remember, I was careful about the words I chose. I said, you can't implicitly ignore an error. That's what I said. This is not an implicit ignoring of an error. This is an explicit ignoring of an error. You can do stupid things in Rust. This is how you do a stupid thing in Rust, right? Rust wants you to be safe, but if you're really insistent, you can do it. Okay. Or run. Okay, so now what we're going to do is we're going to add a dependency. One of the things that makes Rust better than C and C++ and other languages that are compiled, one of the reasons why Rust is really, really successful is because we use so much code that we don't write. And that is very unique for Rust, right, for a compiled language. If you use any dynamic language, you're used to this. If you use Python, you know what pip is. If you use Perl, CPAN, Ruby, Gems, Node has NPM. All of these places are where you go to do all of the work you're going to charge other people for, but that you don't have to write, right? And with Rust, we use crates.io. So again, they're saying here we have a dependency on rand. And if I want to see the documentation for that, I open up a new tab, rs space, !rand. And it's going to open me up the documentation for rand. This crate is not part of core Rust. That means we have to download it. And how do we download it? That's where cargo comes in. So I'm going to add this to the cargo toml file right here. And the second I put that dependency in there, I'm ready to rock. I can go down here and I can go cargo build. And now what is it going to do? The very first thing it's going to do is download it for me. I don't have to worry about anything else. Cargo build. And it's going, see how it compiles it, downloads it, compiles it, it's all there. Okay, so that is super cool. Like, I just did that in 1 second, and you take for granted that this is the first compiled language that really had this functionality. And that's why I think there's a huge market for it, because it brings what we like out of Node to a compiled language.
A specific version, of course.
Yes, yeah. There's both a cargo lock file, which includes the actual dependency version we have, and then there is the cargo toml file, which talks about compatibility. So you can say something like, I need version 0.8.5, then every time you ask for it, you'll get it. Or you can say caret 0.8, and then when a new version comes out, it'll upgrade for you. And whenever it upgrades, it'll relock the cargo lock file. So when you give it to a client, you know that you're always compiling the same code, right? You have reproducible builds. Yeah, it's really, really cool. And so there we go, we've done that. I will also say that you can edit the cargo toml file, and you can always say, I want this dependency at this version. But there's a much easier way of doing that. Let me show you this. If I delete this here, now I have no dependencies in my cargo toml file. I can go cargo add, right? And I can say rand. And now it'll download the newest version. That's it. Now if I look at this, you'll see here, it installed rand 0.8.5. That is the newest version. Okay, let's hit on something else here. When I did cargo add, it didn't just add the toml file. It told me that there are optional features, right? There are things that it's going to give me by default that I don't need, which are these. It's saying you probably want them, but you don't need them. And then it's going to tell me down here, here are things that you're not getting that you may want. This is super cool. This is a feature called conditional compilation. And that effectively means we can enable conditionally extra complexity, things that it'll do that we like. And let me give you an example of one thing it'll do that we probably like. Surday on here is the Rust serializer. So Rust has a system of serialization, which is first in its class. It can serialize the toml, JSON, XML, whatever. There's a plugin for Surday for just about everything. But to work with Surday, you have to have implementations for the Surday interface, which requires you to have Surday installed, right? And what this is telling you is, if you're using Surday and you want to serialize a random number generator, we can do that. Just install the optional feature Surday. Then you can serialize the random number generator. Now, why would that be cool? Let's say you're testing shit and you're generating random numbers. You're going to get a different random number every time. But if you serialize the random number generator, it's going to be to a specific seed. You're going to get the next random number will be the same. So it gives you the ability to serialize the random number generator its entirely and spit it back up at the same state. But that's pretty cool. And that's likely what that is referring to. I don't know, I didn't read the documentation. I'm just bullshitting, but I'm probably right. 80%. Someone can fact check me later. Sounded good. Cargo build, cargo update. Okay, so if we have a version and there's a newer version out, we can run cargo update on it and it will update the version. So let's run cargo update, and of course there's nothing that's new because it already installed 0.8.5. And I guess there isn't 0.6. This one actually says there's 0.8.6. I don't see it there. Yeah, this says 0.8.5. I don't know where it's
My
at.
grade also says it.
What's up?
Mine also says 0.8.
Yeah, so I think they just made that up. They literally just bullshit.
They should have done 8.4.
Yeah.
Or 8.5.
I agree. That would make more sense. Yeah, or maybe someone released 0.8.6, they pulled it back. You know, in which case that's definitely confusing. By the way, I'll tell you right now, if you have the intention of being a computer programmer, what's up?
Expect you to break all the
Well,
time.
it's a productive talk, not that one. But there are 2 different resources you should tie yourself into. One of them is StackOverflow, where you can go to ask someone other than me a question. Though I don't mind questions, but, you know, definitely it pads your resume. It shows people you engage in problems and you know how to get solutions from a community. It is a good resource. The other one is GitHub, where you can obviously file issues and show your work. Because I would say this is somewhat confusing, because 0.8.6 doesn't exist and it was pulled out. If anyone wanted to get a contribution into the Rust book, you've got 40 people racing you for it. So you can always clone it and change that like you said, go from 0.8.5 to 0.8.4 on the install, and then show people how to upgrade to 0.8.5 because that data is wrong. This is not true. Crate hasn't released the 2 new versions. That's not true with the versions they're giving us. You can say contributor to the Rust book. We had a couple of people do it the last class. I do push people to make these changes. Because just think about how often people like go over this book in class. I mean, we beat the hell out of this book, but I don't think that this is very common. Certainly colleges are going to be enamored with Java for the next 400 years. All right, so we are now upgrading our program, right? We are implementing new functionality to our game. Now we're going to be generating a random number, and how do we do that? We use this thing, ran thread RNG, right? That is likely a threaded random number generator, and we call it gen range. And we're saying inside of the range of 1 up to and including 100. So Rust has this special syntax for representing a range. A range is a primitive type in Rust. It is a first-class citizen. It is something you have in the language. You have numbers, you have strings, you have functions, you have ranges, right? So this range is stating 1 up to and including 100. If we didn't have the equal, it would be like every range in every language, which is 1 up to 100, but not including. Equal makes it up to and including. And we're printing out our secret number here, which is cheating. Then we're saying, please input our guess. We're taking a guess, and we are reading it from input into this guess functionality, just like we were before, this guess variable. And if I fail, I'm handling it by throwing a fatal error. And then I'm printing you guessed guess. So we're effectively have 2 disconnected pieces of functionality. We have the first piece of functionality that is generating the secret number, and then the second piece of functionality which worked as before, which is just reading out the input, right? So this is incrementally building up complexity. Now we're introducing this RNG stuff. So I'm just going to copy this. We're going to come over here. I'm going to go tab new, source main. Let's go down here. Boom. Okay. All right. So let's go ahead and cargo build. So all it's going to take is cargo run. Cargo run. It compiles it. It says the secret number is 63. Let's guess 63. It's not going to do anything different. You guess 63. So now we have the functionality there to create a secret and to guess the secret. We just need to say if we're too low, guess higher. If we're too high, guess lower. And if we get it the right, we say good and we exit. Right? So let's come down here. Here's where we're going to handle that. Now we're snipping the top, so they're saying effectively save what you had before. We're going to print ln you guessed. We're going to tell people what they guessed. You've already got that code in there. And then we're going to do the match ordering thing. right? So now we're gonna analyze the data. So we're gonna pop that right here.
You get mismatch types.
Yeah, I think that that's actually.
It's on purpose.
And that's normal. In fact, that's what this thing means in the book. That means that they want you to see that error. So what we're doing is we have this type called main, and main doesn't return anything because main is called by the kernel. So your computer's kernel calls main. We'll just keep it at that. And the problem is that main can only return a number. Your kernel effectively says, what is the status code of the thing that you're calling, right? Status code is a number. So you return a number from main, you can do that, but you can't return ordering equal, ordering greater, ordering less than, because the kernel would say effectively, I don't know what that means. What does it mean when your program executes and you return greater or less? So that's where the error is. And they're telling us here, if we try to run it, we'll get that error. You should trust them, but we'll run it. Hard to run, mismatch types. So it's saying that match guess.cmp, expected string, found integer. Okay, this is a different error. My error comes later. This error is because this is the first one actually. If you notice here, the first error is different than the other three. The first one is mismatch type. The other three are failed to resolve. Mismatch type is an error because secret number, which is right here, is a string. No, is an integer. Secret number is an integer, but guess is a string. Does that make sense? We have two totally different types here. We have a string, which can be any character, an A, a B, a C, a D, 1, 5. That's a character, right?
Yeah.
You can have multiple characters in a string, and then we have a number, which is actually the binary representation of that data. So Rust is effectively saying, I can't compare these two different things. So how do we make them the same? We're going to add to it secret number. We could add something like this, parse, and then trim and parse. That's what you want to do. Trim and parse. What's up?
You're on the wrong line, the trim and parse.
Oh, that's a, yeah, okay. Secret number, so we want to put on the guess.
Yeah.
Yes.
So, yeah, you can guess.
Okay, trim and parse. Now parse may return an error, so I could just do the same thing here. I could go expect, yeah, and then I could say could not parse integer. There we go. Okay, so that's one way to solve it. I don't know if that's exactly the book did it, but whatever. And then we still have these failed to resolve. So the problem here is that we need to specify where they're coming from. So ordering is going to be coming from use for, what did it say? STD ordering? I don't think you need ordering.
It's a standard column, CMP order. It's under CMP and then order.
So there you go. Please insert your guess. Let's give it a high guess, 90. You guess 90 too big. You guess 40 too small. Let's give it the right guess, 73. You guess 73, you win. So now what we have to do is run this in a loop. We have a guess again, right? Does everyone understand how this is working?
Mm-hmm.
All right. So in order to do that, we're going to add a loop in here, right here. And we're going to loop this whole guessing thing, right? And this will work, but it won't give us an exit for the loop, right? So I can just loop this. Now, your secret number is 29, your guess is 29, and it does that, which is crazy. And if I do it again, your guess is 3, and it's still saying you're guessing too small. So what I want to do here is, I want to move this stuff down. Let's move that into the loop. Now, guess the number, your secret number is 14, we'll guess 20, too big. Let's guess 10, too small, let's guess 14, and we win. But even when we win, it doesn't exit, right? So that's probably what you want. You want to keep guessing until you get the right number, and then you don't want to keep guessing the right number, unless you're riding the short list. You're a very, very special individual. You play the same game all day long. So what we're going to do is, we're going to have to exit it. So we're doing that right here. So we add this new thing called break. Break exits the loop, says you're done. And now what we're going to do is say, break, you win, right? So we have right here where it says you win. We're going to put this in a block. And we're going to put right down here, break. Right after it. There we go. Farther run. Your input is 26. Please make your guess. 26. You will. And we're done. All right. So we showed a couple of different things here. We showed the looping construct is loop. That's how we can loop infinitely in Rust. It's very simple. In other languages, even that looks uglier. You have like while one or whatever. And we say when we're looping, we want to do this thing. And when we have the right guess, we're going to use break to exit the loop. And that's our flow control construct. All right. Summary, you are awesome, you win the guessing game. And then it's going to show us the overall thing. Cool. All right, we have common programming concepts. This is chapter 3. Let's go ahead and fill this chapter 2 today. And then I think we'll probably be good somewhere around there. Variables immutability. We already hit that. There we go. So we have this concept of immutability. They're not mutable by default. That's what it's showing us right here. If we declare x equals 5, we can't later assign 6 to it unless we make it variable. Mutable. Here we can, because we made it immutable x. We have a concept called constants. Constants never change. The only difference between, so now you probably raise this in a question, what is the difference between a constant and an immutable variable, right? Okay, so here's the difference. A constant is forever the same, and an immutable variable can be shadowed. That's your difference. And this shadowing is a common thing in Rust. So shadowing means I want to have something else by the same name, right? Because you have something else by the same name, it does not mean you're writing that data to the same location. You just have a different variable entirely that shares the same name. Not the same location in memory, not the same data, maybe not the same data type, but it shares the same name. Constants don't provide you that. Constants have to be unique. So you can't overwrite a constant to be different. And this is where they're going to introduce shadowing, and this is kind of how it works. So if it sounded complex when I was talking about it, look at here, this should be a little bit easier. You have fn function main, and we have let x equals 5, and then I am shadowing that 5 by saying a new x is going to be equal to x plus 1. So that x from that point on is going to be 6. That doesn't mean the 5 is gone. It just means something else is sharing the same name, x. Now inside those brackets there, we have let x equals x times 2. So inside those brackets, that is shadowed again. And now we have another thing by the name of x, and the value of that new thing is going to be dependent on the old value. It's totally fine. A new value comes into existence with the same name as the old value, but it is a different variable. And then that's it. Now there's one other thing that I would say here. All of these are rational semantics. This is kind of an important idea that we understand it, right? So that means that this is giving you a method to reason about your program. By the way, I'm sorry, I'm gonna sit down for a little bit because I have sciatica and it sucks. So what that means is that when we look at that program, right, you can understand what your contract is with the compiler. You can say, I know that at this point, this X is referring to something different. The compiler can do whatever it wants. It is only concerned about the effect, right? So what do I mean by that? I mean, all three of those X's could be in the same location. Why? Because that's not true. We revisit this one. So this one here, at the very top, let X equals 5, could be totally temporal. The next line could be written to the same piece of memory. Then this line here could be written to a new piece of memory. Then this line here could refer to that same piece of memory at the top, right? So this one doesn't have to live. Let X equals 5 does not have to live beyond this point. This one has to live because it's used down here. Okay? Now your head is probably fucking mush.
But we have like 3 versions of X right now in this example. Three.
You have 3 conceptually different X's. You have shadowing that makes a difference there. But in practice, the compiler only guarantees the effect. And what I mean by that is, sometimes when you declare a variable to be immutable, if it's never used again, the compiler can still write to it. There's nothing wrong with that. The compiler knows better in many contexts. So you don't know how that's going to actually get optimized. When you compile something, especially when you use that release flag, Rust is going to analyze the shit out of it. And it's going to do what is the fastest. It's not going to break the contract you have with the compiler. But the compiler is going to say, I know what this is going to end up doing. I know this X up here never gets used again. So I'm going to put this one in its place. That make sense?
Mm-hmm.
Okay. Because if you see all this stuff and it says mutable and immutable, that's for you, right? That's for the contract downstream. The compiler has optimizations that blow your head off. You know, they're really crazy. And you actually have to look at the disassembled code to figure out what it's doing. And that is an art in and of itself, and we will do that art later on in the class. You know, it's way too geeky at this point. But we'll look at that in something called Godbolt's compiler later on in the class. And we play around with this stuff. I usually have a special little subclass I do on guess what the fuck this is doing and you're wrong. And it's a lot of fun because no one can ever figure it out. What's up?
What you have highlighting, that's shadowing?
The one at the top is being shadowed by this. That means you're supposed to have 2 different immutable pieces of memory, and the second one, that X, says, I'm now going to be known as X. I'm shadowing the name X. I am a different variable, but I am now going to be known as X. But the compiler can say, even though you're supposed to be a different variable, I know the first one's not being used, I'm going to write it to the same memory address and save some time and space.
And it does it because it's immutable by default. In order for it to be mutable, you have to put the MUT, right?
Okay. Good question. So if you want to write to the same location as the first one without shadowing, then you are right. This one would have to be mute. What else would have to change? What else would have to change? Okay, let is a declaration. It's declaring the X, right? So if you're going to make the first one mutable, then you can no longer declare X if you want to write to it. If you don't remove the let, you're still shadowing.
Okay.
Let is the declaration for the variable. If you're writing to a mutable variable, you say X equals. You don't say let X equals. The second you introduce let, you could be potentially shadowing.
So declaring, right? You're asking for more.
Yes.
So every time you shadow something, the prior version of it, it is no longer referenceable or used, right?
Every time you shadow something prior version is no longer referenced. In that scope.
There's
It
very
can come
called
back.
X, you have no way of referring to it.
Okay, let's look at this one more time, right here, right? Right here, it comes back. So here, this one is shadowing this, right? So this is inside of a brace, it's being shadowed now. This is now what this will see as X. This print line, which is printing X, will see this one right here as the X. But when this brace is over, when this scope is over, what's going to happen for this one? The shadowing is done. So it's going to see what it was last seeing in that scope, which is up here. That's your exception.
And you'll never go back to the original x equals 5. You'll never need or it would not be possible to reference that because it's been shadowed and.
That's exactly right. Because it just so happens, we're not calling it. And it just so happens that the compiler can very easily see that and pull a quick one on. So this is one area where you're declaring it to be immutable, but the compiler is going to see it, know it's never used, and likely just write to it again. Yes.
And that's because it's in a different scope or context.
Yeah, it's
I mean, it's in the same.
It's in the same scope. of context.
Right,
Yes.
but
If it was
the other
in-
one's in a different scope context,
Right.
so it's not gonna go to that same memory location.
That's exactly right. Because when that scope is over, it means to still have the old value. That's exactly right. All right. Anyone else have any questions? All right. Let's talk about method calls, right? So we saw before how we created a string, which was distinguished the difference between the type, which was inferred. We didn't have it by default. And then we created this thing with string : new, which says I need a new string, right? Now, strings don't have, when you see something like .len being called on that string, right? You can think of string as an object, right? You can think of string as an object and .len as a method. In Rust, we never call them objects. But anyone who's coming from another language will see that and say, that's a method, string must be an object. And it's close enough. Rust has a very small distinction, which we'll address later, exhaustively, about the differences between a struct and an object. Right? Rust is a newer generation language, and it has gotten rid of objects entirely in preference for structs. So there are no more methods, and there are no more dispatches, and a lot of that stuff is just gone. That's a different way of slaying that dragon. All right, so we have let spaces equal spaces.len. So here we are shadowing spaces. We no longer have access to the original data. We just know how big it is. And here we're saying let mutable spaces equals the string, which is just a set of spaces. And we're saying spaces equals spaces.len. This will not work because a variable is mutable means you can write something else to it, but it is still typed. Cannot change the type, right? So spaces is a string. You cannot write a number to it. The length is not a string; it's a number.
Right.
You're going down. That would work, yes. Data types. All right. So let's go over these really quick. We have already seen the parse expect notion. And parse relies on type inference. That's kind of cool. So you can have type inference going both ways. The first time we saw type inference, we saw it because we had that secret number and we had it untyped, right? And it was pointed out that it was a string and we were calling string new on it, but we didn't explicitly say it was a string. String new, well there we go, it's a homonym. String new that the type it was set in was determined by the call to new, which was a string. Here we have the opposite way of type inference happening. We're saying guess is a U32, therefore parse it into that. We don't have to tell parse to parse it into a U32. Parse knows the output must be a U32, and it infers it the other direction. It is super nice. That was the comment, and that is in fact true. This is why Rust is a very loved language. It does the simple things very simple, and it makes the hard things way simpler than in any other language. The rough area is the middle ground. It's that chapter 4 and 5 we're going to get to. We're doing the borrow checker or whatever it is, you know. You got to get through that. I'll lose half the class, but it's worth it, you know. You can wrap your head around that and join the elites. And you can open, rewrite it in Rust, bugs everywhere. Yeah, so we have this notion of a scalar type, and a scalar is any one thing. This is a term you don't see often used anymore. Perl has it everywhere. But a scalar just means any one thing. Rust types the scalar, so you don't have a notion of a scalar as a one thing. You have a notion of a one thing that's an integer, one thing that's a float, one thing that's a string, one thing that's a function. All those are possible, but you have to say what that one thing is. In other languages, like in Python and in Perl, not really Python, but in Perl, that type is just simply scalar, one of the things. And we'll get to where that makes a difference. Here we have different types of integers. Let's focus on this for a second. This is pretty transparent. It's not enough to say you have an integer, right? That's perfectly fine in TypeScript. TypeScript is a very high-level language. Rust gives you the ability to do everything TypeScript does better, and it has the ability to write code in a lower level, right, for things like the kernel. And why is that necessary? It's necessary because the smaller the integer type, the fewer instructions that are required to use it. So at the lowest level, this makes a huge difference, right? You want your types to be sized properly. If you make everything big, you'll find things just so happen to run slower, right? 64-bit instructions take more opcode than 32-bit instructions. And 8-bit instructions are sometimes done with one opcode. That's why increment is so fast, right? So Rust has all these different types, and the compiler's going to take care of all of them. You just have to say what you're storing, right? And let's go through that. We probably don't go into binary in this, and that's probably good. It's sending me way into the weeds. But you have this notion of an 8-bit type, a 16-bit type, a 32-bit type, a 64-bit type, a 128-bit type, which by the way is massively slow, and architecture optimized types, right? Where you can say, depending on whether or not this is a 64 or 32-bit machine, I want the type that it operates best on. If you don't know how to figure out the min and the max of these, you can just raise 2 to that number. So the max for an 8-bit type is 2 to the 8. Max for a 16-bit type, 2 to the 16. Right? So just run the math and we'll figure it out. Now, it's not even enough to say how many bits that type has, because you also have signed and unsigned. By the way, if this is complex, then C is insane. This sounds complex, it's so much less complex than C. You don't have to worry what the fuck a long means, you know, or double long, or all that other kind of crazy stuff. You at least have very clearly how many bits the type is, you know. So that to me is at least somewhat nicer. And you have this notion of unsigned and signed. And the difference here is that if you're storing just positive integers, you're going to use unsigned. And if you're storing negative integers, or things that could be negative, you can use signed, right? And what signed effectively means is that, yeah, we'll do that some other time. Depending on what you need, your ranges are different, you know? We've done a whole classes on this too. It's kind of an interesting topic, but I think I would get in the weeds too quick if I was to explain it, because computers have a different way of doing this. But if you don't need negative numbers, use unsigned always. If you need negative numbers, go for signed. And you can always go too big. The only thing that'll happen, your program may run a little bit slower, and it may be a little bit bigger in memory, you know? All right. Let's talk about this. And by the way, I'm sorry about some of that stuff, because I want to have an area where I set the bounds up and just stay a little bit closer on Rust, especially if no one has an interest in it. And I want to get through this big escrow. So we have decimal. Let's take a look at that. This is a nice little nicety that Rust has. We have the ability to put an underscore in where the comma is in English, and it ignores the underscore. So this makes it a lot easier when you're reading a 6-bit, you know, a 6-character number, to know how to read it. And I like that feature a lot. All of my numbers have that. You know, I use that everywhere. That's a good feature. A lot of them just do it. I like it. Hex is going to be 0x. That's pretty normal. If you've ever done hex work, hex programming, that is everywhere. Octal is 0O. That is not normal. Hope you don't have to do octal programming. It is really weird. But yeah, it's just unique for the Rust thing. Binary, this is also beautiful. You can actually learn binary with Rust very easily. I love that syntax, 0B. right? And you can write your string out in binary. So if you're having you have an unsigned 8-bit integer, you can actually write this just like that. The unsigned 8-bit integer equals 0b1111_0000, and it'll throw it in there just like you see it. So sometimes you can write your actual binary value in binary. This is amazingly useful when you do reverse engineering or you do low-level stuff. Byte U8 only. This is setting it to a character. These are all consonants. They're consonants? No, constants. There we go. Literals. That's what I would say. These are all literals. So this is the syntax here for literals. Byte B single quote A. That's going to say assign it the single value, the ASCII value of capital A. Right? Okay. Let's go over overflow really quick. Overflow is something Rust can protect you against, but chooses not to. Some languages always protect you against overflow. So what does that mean? Rust doesn't force overflow protection on you. You're probably used to having overflow protection. When you run something in debug mode, it doesn't actually, it will check for overflow. If you run something in release mode, the checks are gone because they come at a runtime cost. What does that mean? When we talk about an 8-bit integer, we have 2 to the 8 powers of values we can put in there, which is 256. You ever look at an IP address and you see 255, you include 0, that's 256. 0-based, right? The reason why an IP address is only up to 255 is because every one of those octets, that's number, dot number, dot number, dot number, is 8 bits. The whole thing together is 32 bits, right? That's how that works. It's a good way to think about that. So what happens if you have one of those octets at 255 bits and you add 1 to it? If it's signed, it's signed, and 0 if it's not. That's exactly right. So, yeah.
If it's signed, you didn't get up to 255.
Yeah. I don't want to go. Yeah. There's definitely a nuance there. It's a good catch. Yeah. We're gonna drop it. Let's ignore that. It's tempting, but what I want to say is that it rolls over, right? So the rollover effect can be interpreted in different ways, but when you add 1 to the maximum value, if you don't catch that error, we would say you rolled over, you overflowed, right? And that's what it's doing here. So it's telling you that if you run it with the debug mode, you'll catch that. And that's true. Floating point types, okay. So let x equals 2.0, let y equals 3.0. We're showing you here that the default floating point type is 64 bits. You also have 32 bits. Why would you want to use 32 bits? Can anyone take a guess? Space optimization, and it's faster. That's it, right? So if you know you don't need the extra precision, you can run it in 32-bit. That's exactly. It's very simple. It's not complex. But if you don't care, just leave it at 64. There's no difference. Numeric operations. We're showing you here. We can add, we can subtract, we can multiply, all that kind of stuff you're probably used to.
Is there a difference across users?
Is there what?
Is there type difference across the user codes? If I declare anything, I try to subtract from
If you declare an int and you try to subtract a float, yes, that will generate an error. The answer is very nuanced there. It's going to be when it's safe, Rust will allow you to do it. And when it's not safe, Rust will force you to use the keyword as. The keyword as says, I want to take this number and interpret it in a different context. Or I want to take this number and...
It's a typecasting.
Yes, it's effectively a typecasting. Yes, it's an explicit typecasting. So you can, for instance, you can take an unsigned and a signed. Rather, you can take an unsigned 32 and an unsigned 32 and assign it to an unsigned 64. You can take an unsigned 32 and an unsigned 16, add them together and assign it to an unsigned 64. Rust knows these things are possible and won't complain about it. But if you try to go down, try to take a 64-bit integer, unsigned, and go to a smaller size, Rust will go, what in the crap, I can't do that, there's a problem, a potential problem, stop, and you'll have to say as. And then Rust will say, okay, I'll just ignore those bits and do what C does, you know, something like that. So, yes. And here we go, main. Now we're looking at Boolean types. We have this true and false. These are very simple. Character types. So we have the notion of a string and we have the notion of a character. A character is one thing. A string is multiple things. Pretty simple there. But, yeah, let's also go over this. So they're showing you the cat face there, hard-right cat. And the important thing here is that the Rust notion of a character is UTF-8, right? So it has, I think a character is 32 bits, right? Because it's storing UTF-8 data. So when you say I want to have a character and then heart-shaped eyes, you get 32 bits to store with because you could be storing UTF-8. So any UTF-8 character will work there. Compound types, yes, tuples. All right. So tuples are also typed, and they also can't change types. So here we have a tuple of 3 different things: a 32-bit signed integer, a 64-bit float, and an 8-bit unsigned integer. And we're assigning it these values: 500, 6.4, and 1. And this is nice because this is strongly packed. It's super efficient. Python also has this. Rust is even better. Not going to go into why. But yes, it's very simple. It's just as simple. Tuple, here we have another one. And what we're doing here is we're showing what we would say is deconstruction. So we are deconstructing the tuple, which has 3 different variables, 500, 6.4, and 1. And we're assigning that to new variables, x, y, and z. Right? So let's go up. Let's take a look at that. Let's go through these 2 things. Here we are assigning a tuple of 500, 6.4, and 1 to this, which is a tuple type, right? Let tup equals a type of tuple with these numbers. Here, we're doing the same thing. It's inferring the type. And then we're deconstructing the tuple to assign them to x, y, and z. It's like, I want to know those things by actual names, rather than calling them as the first member, the second member, and the third. Okay. And here's how we call them by the first member, the second member, and the third. Dot 0, dot 1, dot 2. Simple. Array. Arrays are different than tuples. Tuples have a set definition. And arrays, yeah, let's leave that for now. They're arrays. Like Rust has actual arrays. So here's what we're doing. We're assigning arrays and we're putting it in all of the different names of the month. And then I'm saying right here, this is another array type notation. I'm saying I32, 5 elements, right? So you're telling it how many elements you want in that array. And I'm saying they're 1 through 5, right? Let A equals 3, 5. This is going to 5 different elements of 3. These are just shorthand syntaxes. You probably won't use these that much, but they're good for geek points, right? And you're going to have a super ridiculous ego if you're going to open up rewriting Rust issues. So this is highly important. Yeah, so these are just methods of saying I want the thing to be this size or I want this many elements of this type. You had the option to set semicolon 5 rather than writing it independently, right? And it's actually used quite a bit in lower level stuff. Why? Because sometimes you want to explicitly say I need to have 30 bits of 0 because that's what I'm required to send first. So you can very easily do that without writing 0 30 times. Accessing array elements, this is very easy. Like in most languages, you just use brackets. Bracket 0, bracket 1, you get to the element number. Invalid element access, this is kind of interesting because this gets caught in compile time no matter what. If you try to access an element in the array that isn't valid, Rust will not compile. It'll let her out and say, that doesn't exist. That array isn't of that size or area. Cool. Any other questions about data types? Knocking it out. We're at 8:10. Functions. All right. Functions in Rust are also strongly typed, And what does it mean to have a strongly typed function?
What it returns,
Half of the answer? What's the other half of the answer?
what it takes in.
There we go. It's the other half of the answer. Now you got 100% right. So functions can be strongly typed. For you to have a strongly typed function, you have to know what that function takes and what it's giving you back. And it tells you exactly the type of that function. In Rust, we have to specify both. It doesn't infer that, right? Now, it will infer what you're returning based on how you typed the function. Okay? So there's still inference there. It just will not infer the type signature of the function. You have to provide that. Okay. No.
So you can't manipulate a function that does one thing that's integer string.
What you can have it is accept it a generic. It can be either one of those two things. And then the function can accept the generic. And then it gets put out the same way. All right. So this is nothing special here. We are declaring a function that takes an I32. And notice that there's no arrow here. There's no arrow here. So if there's no arrow after you see this end parentheses, then it doesn't return anything. It takes in a value and it returns what we would say is a unit type, nothing. The unit type is implicit. So it's not inferring what the output is, it's just simply saying there's no output. Okay? Pretty much, yeah. You can think of it as right here. Print labeled measurement right here, we're calling this with 5 and an H. And here we're saying the value is an I32 and the unit label is a character. So we're golden, that works. Statements and expressions. Okay, this is kind of interesting to me because languages define these things differently. These terms are highly argued out. But let's go and look at this definition because I don't use it, but that's how the book uses it in Rust. So statements are instructions that perform some actions and do not return a value. Expressions evaluate to a resultant value. Look at some examples. I think the way Rust defines a statement is also about a semicolon. A statement comes something before semicolon. So here we're saying let y equal 6 as a statement. And what they're showing you here is that this doesn't return anything. In some languages it does, like Lisp. But in most languages it does not. So let x equals and then let y equal 6 doesn't set x to anything. It breaks. Else than that. Yes, else than that. It's also kind of funny too, because after you use Rust, you just assume everything fails to compile. You don't really remember what a warning is because there's so few of them. Like it is just gigantic. It can be a pain in the ass. You know? It will just simply fail to compile if you make a mistake. Even in like that case, you know, you can think of alternative behaviors, but it doesn't bother. It just simply fails. Okay, and then I just screwed the browser. Yep, here we are. All right, so now we have something slightly different, right? Before we were, let's take a look at the two and compare them. We were using parentheses to try to get the return value of a statement. Where is the return value of a statement? Now we're using open brackets. Open brackets create a block. A block is an expression. The expression returns the last thing you evaluate. This is also the way a function works. A function's body returns the last thing that it evaluates. So this is one big anti-pattern in Rust, is people that put the semicolon after the very last statement in Rust, right? The very last expression in Rust, that makes it a statement. Then Rust always returns a unit type for that function. It'll error, it'll tell you, this isn't right, you know? And we'll see that probably in a little bit. But just remember that you likely don't want a semicolon on the last thing in Rust. And you're seeing here this expression, let x equals 3x plus 1, it's going to return x plus 1, which is 4. That's what that expression will return. You don't need to know.
But if you really like semicolons, can
You can, there's other ways you can specify return value, yeah. I mean, you can specify the type over here of y, and then it'll infer, right? So if you want y to be set to a specific type, then up at the top right here, you can specify the type that y is, and then it will infer from the parenthesis, from y's type, what the return value is. Does that make sense?
I was talking more about
Okay, we're not on functions yet. So when we get to functions, show me. Here's functions. What do we got here?
Yeah, there's no return.
Yes.
You don't actually say like a return thing.
Okay, good. So yes, some languages have required explicit return, right? In Rust, you don't require explicit return. You can provide an explicit return. You would provide an explicit return that used Rust before me was ironically Carroll, the fencer. Yeah. Anyway, so here's a simple statement, comment, hello world. And here's where you're saying all the different comments here. We're showing a multi-line comment with a bunch of them. And here we're showing you that you can do a comment after the statement. And down here, I'm showing that you can do a comment in the body. Now, that is a really unfortunate check. That sucks. What?
Why is that?
Yeah, because Rust is the kitchen sink when you need it, right? So it's got cargo for you right on the get-go. You'll use it all the time. Cargo has something called cargo doc. It will generate documentation for you. In my opinion, one of the best things about Rust is the culture for documenting, testing, and sharing code. And the reason why the culture is so good is because there is zero ramp up to those three things. Those three things are high priorities for the language. Not prime priority, but they're high priority. You'll see more attention put to those than any other part of the language. Let's take this here as an example, right? Let's come down here, let's yank all this stuff out, and then let's just say right down here, and I'm gonna say fn do game, and then I'm gonna open it, and then I'm gonna pop it, and then I'm gonna paste all that stuff. We're gonna write it, and I'm gonna come down here, and I'm gonna say do game. No underscore. Okay, now, this is horrible. I just moved everything out of me and I put it all in the do game. What I want to show you is if I come down here and I put 3, right, I can say, this is the do game, guessing game. Give it any number. No, it will generate any number, generate a number. And then you will guess at that number until you get it right. Okay. Now, I write code in a lot of different languages. I find myself documenting Rust more because it sucks so much less. This makes a huge difference. You go cargo doc, right? And it's going to generate the documentation for that. Now I'm going to take this right here, this link right here, and you're going to notice it looks like all the other documentation for Rust. It generates you the doc for it. So there's do game. This is the do game. This is the do game guessing game. It will generate a number between 1 and 100 inclusive, and then you will guess at that number until you get it right. And you can click on it, and if that's a public function, it'll actually show it to you. But it's showing you here the lock, so you know it's a private function. So a library can't use it. So it's telling you the visibility, public or private. It's telling you what the function is documented for. It'll even show you if it's a public function, what how it looks, right? So if I go right down here, pub fun. Let's do that again. Now the lock is gone because I made it public. And you see here public function do game. It accepts nothing. Right? So I'm saying all that documentation is already there for you. It's super cool. And it immediately can work with things like the Rust extension, Chrome extension. It's awesome. And then you share it to Cargo, or you give it to an employer or whatever, you know, they can see all the documentation for your code. And the only thing you do differently, right, is use 3 slashes instead of 2. So an internal code comment is 2 slashes. A documentation piece is 3. And what I find myself doing in every language is documenting my code extensively internally. But when I find myself using Rust, I document all of my code for external use. I show what I want other people to see when they're reading that code. So that to me is a big loss in that chapter, that they don't explain that right off the bat. It's a huge selling point of Rust, in my opinion. Don't discredit documentation. It's worth its weight in gold. So,
like a neat IDOC standard equivalent request. It's like a very stringent documentation on the function and given it.
well, that's because Python, well, Python now has type hinting. So there is PEPs that pertain to type hinting that make you forcibly use type hinting. Type hinting in Python is done horribly wrong. They had a huge brain fart and just ran with it for years. But in Rust, we have actual types and they're required. So there is no need to document that. You can never run Rust code without types under function. So the Rust function typing for this, the function is already there. And when you generate the documentation, it'll generate it. We even generate it without comments. If it'll always generate the most documentation it can automatically, they can generate a lot of really good documentation. All right. So 3 makes it a doc comment, and then you can even come up here and you can document the whole thing, right? With this, you can say like, this is my module for each line, right? And I can come down here and I can say cargo doc. Come down here and I can go down here to my guessing game, and we can say this is my module for each line. So you have this notion of like module documentation, function documentation, and it can be, by the way, let's go down here into function. We could even say something like here, this is the secret number I generated. Well, that didn't actually work. Yeah, it doesn't do that. It only doesn't do it inside the function. But it'll do types, it'll do functions, it'll do structs, it'll do enums, anything like that. You should doc on it. All right, and then the last one is control flow. We have plenty of time. Okay, this isn't all that bad. If expressions, this is kind of where I think this definition of a statement is a little more interesting. This is, in fact, not a statement. This is an expression. It is an expression because it's returning something. So main will return the result of this if statement. Now, what is the result of this if statement? There are 2 different print line components there. Print line will always return the unit type, right? So it's just effectively doing nothing. But it's showing you that the if expression returns something for us. Let number equals 3. If number, print number was 3. This doesn't work because number is not a bool. Right? So number, you expected a bool and found an integer. That's not going to work. You have to have some kind of conditional that evaluates to a bool. By the way, that's how conditionals work in Rust. They're not magic. So when I say if number equals 3, number equals 3 literally returns to a true or false value. You can set a bool by using a condition.
A lot of times, underline you that condition will be fine. You just say if that thing
It's true.
or is null.
Yeah, whatever the truthiness is defined as.
But in Rust, how would you do the same thing?
You wouldn't do the same.
You would absolutely say if this thing exists, right? So like if it didn't result in error.
Because think about the whole notion of existence and non-existence. That requires you to have a way to express non-existence. And you can do that in Rust, but you have to explicitly do that in Rust. No type has a notion of non-existence. There is no null type. So a number can't be set to null. It has to be a number from the moment you declare it. In C, you have the option of ignoring the type and setting shit to null. That was a bad idea. By the way, the guy who created C said that was his only $1 billion mistake, which is delightful. But yeah, he's very proud that was his big one. And it is a huge mistake, because you have a notion in Rust of having what we would say is a parameterized type. You can have a type that is maybe or something, right? That represents an undefined value and or a defined value, but it's not part of every number. It's a different thing. We'll also get to that. All right. So number equals 3, if number is not equal to 0, if number is not equal to 0, good. These are just conditionals, if and else if. Does anyone here not understand if and else if? Okay, we're jumping through that then. Using an if and a let statement, this is interesting. Ifs return a value, I remade that statement, because they return a value, you can set something with them. So we're setting the number equals to the result of this expression. If condition 5, else 6. Right? So in this case, condition is true, that's getting set to 5. So your question? Yes, it is effectively returning. Ternary is an if statement in an expression, right? And this is the fact that you can put any if as an expression, or that an if is an expression, means you don't need a ternary, so they don't exist in this. All right. Cargo run. Condition 5, else 6, so yes. So this is also interesting too. In the first example, both sides of the if statement, when the condition was true or false, returned the same type. Rust checks that. So in this one, they're showing you that you can't return on one side of the if statement, the true side, 5, and on the other side, the string 6. Because nothing can take a 5 or a 6 like that. So it's going to error. And it catches that. It does some crazy stuff. It has exhaustive pattern matching, is the way that Rust implements this. So if you have an enum and it has 20 different things on it, and you accept that enum, you have to handle all 20 different values for that enum. Yeah. It's interesting how it works, but it does work really well. And it'll tell you if you forget one, if you made a mistake, you forgot handling this. You know? And by the way, that thing, if that sounds okay, that's great. That's how a result is, right? A result is either okay or error. That's an enum. A result is an enum. And the fact that you have to handle an error isn't unique to result. It's just because you're getting an enum back, there's 2 different branches on that enum, an okay and an error, and you've got to handle both of them. So it's the same primitive functionality everywhere that creates all this cool stuff that we like. Let new counter equals 0, let result equals, and we're looping. Okay, this is kind of cool. So we already stated that if is an expression. Well, loops are also expressions. They return the last thing, which is, in the case of a loop, what the break out. So when you hit the break, and you say counter times 2, that's what you're going to return. That's the result of that loop. So that loop evaluates to that last statement break that you broke on. Rust has loop labels. It's nice to know these exist. I try really hard never to use them. I suggest everyone else does too. Loop labels make everything more complex. I'm not saying you can't use them. I don't use them. You know, so it is what it is. There's almost always better ways to write it. Cargo run. And it's going to do what we just figured out. Conditional loops with while. Okay, so we have this notion of while number is not equal to 0, we're setting number equal to 3. While it's not equal to 0, print the number, and then subtract 1. So it's going to keep doing this until it gets to 0, and that's going to say liftoff. This is a countdown routine, right? So if you give it a number that is 0 automatically, it's just going to say liftoff. That's a conditional loop. It may never run. Looping through a collection with for. This is what I just said about Python, right? I said Python gives you this really nice way to model your programs, break down complexity using this interval approach. Well, so does Rust. And here's how that kind of works. We have here, we have this array, 10, 20, 30, 40, 50. Let mute index equals 0. While index is less than 5, print. The value is, and then we say a index. Don't ever do that. That's a horrible idea. Why would they even show that? I don't know. You will never see that. Okay, just say that it's stupid. Good. So here's the method you'll always use in Rust.
What's the horrible idea?
To iterate with an index. You don't ever iterate with an index in a language like Rust. You always just iterate over the thing that you want, and it'll just give you the element back, right? If you need an index, there are other ways to get it, and we'll get that in a later, I'm sure, I hope. Or we'll geek out later, you know. But this is the right way to write the code, right? So here what they're doing is let A equals, and they're giving it the thing, and they're saying for each element in A, right? For in, that's your iterable. You're iterating over A by assigning every different thing to an element.
Is there like an index of function?
Index on functions. Yes.
Give me the index.
Yes, there is. Yes, there is. Okay, and that's it. So we have one more thing that we're doing here. For a number in 1.4, we already said 1.4 is a what type? Range type. There we go. 1.4 is a range type. That's a primitive type in Rust. It's a core type. So here I'm saying in 1.4 is a range type, and we know it's a range type. What is .rev? It's a method on the range type. So rev means rather than iterating through it from the front to the back, iterate from the back to the front. And that's what it's doing. So rev is changing the semantics of iteration for that range type. Range types are iterable. When you iterate over a range type, you start at the beginning of the range, you go up to the end of the range. Rev says, rather than iterating in that direction, return a new iterable in the reverse direction. That's all it does.
It's a range object or something.
Kevin,
So
which
the range is a struct. There are no objects.
Kevin, what loop type is considered the higher performing within Rust? Loop, for loop?
Non-conditional.
Well, for loop, yeah, that's a complex question. And fundamentally, it's about what you need, right? Like a regular loop doesn't have any overhead because you're not assigning anything. So just for doing nothing, that's the quickest. But it also does nothing, so it's finding how much you need, you know?
Yeah.
But you don't really have to worry about that stuff because Rust's compiler is ridiculously good. So just write your code however you feel most comfortable and run it with the release flag, and it'll be faster than anything you can write in most any other language. Reasonably confident I can say that. All right, so we're all the way done with chapter 3. Does anyone have any questions? This is kind of the pace that we'll probably proceed up with the rest of the class.
What chapters should we be ready for next week?
Ready.
I think we
You know,
will
like-
likely do 4 and 5 next week. It took us this long to do 3 chapters, and one of them was an introduction. So I can't see us doing more than 2 chapters a day to pace this through.
Okay, just wanted to read through in advance.
So you can read through 3, but we will almost certainly not do 3. We will almost certainly do 2. And then we'll have whatever time remains is just time to chill. Just so we can go over the timing of this class again, we start at 6:30 sharp. I don't mess around with that. So come here at 6 if you want to get pizza and Coke, or bring pizza and Coke into the meet, and then we'll try to be here and kick things off right at 6:30. All right. Anyone have any questions? Anyone have any difficulty installing Rust? We had some people that didn't have Rust. Is there anyone need any personalized assistance? Containerize everything. Cool. All right. Awesome.
Just use an eggshell.
What's up?
Set up lazy too.
There you go. I converted someone to lazy man.
Pretty sick actually.
And I just converted last week, so I'm already spreading that. You see, Marco, you've never seen lazy man before.
No, what are you all talking about?
Lazy bit.
This is lazy man. Marco.
Easy bit.
Marco is.
What do you all
is
say,
the
lazy
resident-
what?
Vim.
Vim?
It's a NeoVim
Vim.
package, pretty much, and it packages up a bunch of plugins
Ah.
for a nice, easy start.
Maybe I should try that. I've been meaning to convert to NeoVim.
Did you Docker your VS Code?
Yes.
Bullshit.
Want to see it?
You flat back or you Docker? How are you sharing VS Code with your